Assalamu alaikum everyone. So today we will be having lecture 19 and we will be going through the stuff which we have studied so far. So recap 2, right? So in the previous recap we discussed about number systems, conversion between different number systems, complements, right? And now we will be going through Boolean algebra, more logic functions, minimization, and so on and so forth, but we have to be very quick, right? So let's move to Boolean algebra straight away, right? When we talk about the formal logic, right? So for example, if I have to say something that today is such a day and it should rain, right? Or it has to rain, right? So at the end of the day, I have to make a conclusion on the basis of this statement, right? So that is what the formal logic is all about, right? A statement, a proposition that has to be conclusive, right? And it should be true or false. We can say yes or no, right? So our computer system is based on this formal logic, right? And in order to use that formal logic, we define variables, Boolean variables, and those Boolean variables, they can take two values, right? As we are talking about the binary, so they can take only 1 and 0, true, false, yes, no, right? Right? So this formal logic is the basic building block of our computer system, right? So next, Venn diagrams, right? So whenever we talk about the formal logic and we have to be conclusive, so we need some axioms, right? Some basic rules, some principles. On the basis of those different rules and principles, we have to make certain conclusions, we have to make certain, we have to deduce something, we have to induce something, right? But we need some laws and axioms, right? So I have represented those different laws and axioms by using Venn diagrams, right? So here you see A or B, right? Union. We normally replace this with a or we can also use a plus sign, right? So A or B, right? So you can see that we have the colored area, right, within this rectangle, right? So here A intersection B, so you can see that we have a common area, right, that A and B had, yes, right, has, right? So here we have the first De Morgan's law, right? A union B whole complement. So if we have A union B this, right, colored area, so that the exterior of those circles within that rectangle, right, in red, it represents the complement of A union B, right? So here we have the same Venn diagram, right? But interpretation is different. You can see here we have A complement, right? If I talk about A, right, and B complement, right? So here this is the complement of a single variable of a single set. So this is A, and the exterior of this circle within this rectangle is A bar, right? So this is another law, another axioms, A, right, plus A bar B is equal to A plus B, right? So let's move here, right? If we have two circles, one representing A and the other representing B, right? So if I take A complement, right, as the horizontal lines, so you can see that the horizontal lines are not being passing through this circle, right? There is no horizontal line, right? But we can see the vertical lines, right? So if I take B complement as the vertical lines, so you can see that if this is B, then the B complement, right, the vertical lines are not being passing through this circle. They are here. They are being passing here, right? So A complement and B complement, but those horizontal and vertical lines, they are crossing each other outside those two circles, right? So here we have the intersection. So A complement intersection B complement, this is the exterior area, right? But if we talk about the A complement, right, or we take the A complement as horizontal lines, so they are being passing through here, right? Okay, so actually Boolean algebra is a tool that we use in order to simplify our logic, right? For example, if we have this expression, this is the Boolean expression, right? And we have to implement this Boolean expression, right? So we need gates, right? So I'm not talking about the logic of those gates, right? So you can see here we have 1, 2, 3, 4, 5 gates, right? But we can implement the same functionality by using less number of gates, right? So here we have used those axioms, rules, right? And Boolean algebra, you can say, and I have simplified, and I am using only 2 gates, right? So you can see this and this functionality, they are equivalent, right? Then the basic logical operations, right, within the Boolean logic, they are 3 basically: and or not, right? So normally we represent and by a dot or by a plus sign, and not by a complement, right? So these are the basic building blocks for the logical operations. All other logical operations, they will be having and or not, right? So this is the whole story, right? Here you can see we have different axioms and theorems. We have commutative law, associative law, distributive law, consensus theorem, De Morgan's law, right? These are the axioms: x dot 0 0, x dot 1 x, right? So x dot x x, right? So x dot x bar complement 0. So and then we need a representation conversation, right? So here you can see that we have if we have a circuit, we can have the Boolean expression, and from this circuit we can also draw the truth table, right? If you have a truth table, you can go for the Boolean expression, or you can also have the circuitry, right? So you can see arrows, right, connecting those different units. Circuit, from a circuit you can go for the Boolean expression, and if you have the Boolean expression, you can go for the circuit, you can design the circuit, and you can also draw the truth table, right? Whatever is convenient for you, right? Right. But one thing I want to mention over here, that we have a unique representation regarding the truth table. We only have one truth table for a circuitry, right? If we have a truth table, we can draw number of circuits, number of different representations, right? Similarly, if we have a truth table, we can have number of different Boolean expressions, but a truth table is always a unique representation, right? Okay, then we have the NAND gate. If I put a dot or bubble at the output of the AND gate, what it will be? It will be a NAND gate. So this is the truth table, right? So you can see whenever we have 0 0, we have 1, right? So it is a 0 sensitive gate, right? So whenever we have a 0 at any one of the input, we will be having a high output, right? And so this is 0 sensitive gate, right? So if I want to have a NOT gate, so you can see that I have joined the inputs, two inputs, and I have the NOT functionality, right? So I will be using the laws or axioms which I have mentioned before, right? So here I have a dot a whole bar, so I will be using De Morgan's law. Break the line, change the sign, so I will be having individual. So a bar plus a bar is equal to a bar, right? So you can see I started from here and I got this, so this is the complement, so it means this is the functionality of a NOT gate. Similarly here, if I added, right, so this is the NAND gate, right, with two inputs, and I have added this one here, right, so it means I have another NAND gate, right, so this is what, a dot b whole bar, and after this we know that a b double bar and double bar cancels out, so this is the functionality of an AND gate, right? So we will be getting what? We will be getting AB, right? And then we have the OR gate, right? So if you, so we have A bar, B bar, right? And here we have A bar dot B bar, right? Whole complement, right? So A double bar, break the line, change the sign, so I have to replace this dot with plus, right? Okay, so this is the functionality of an OR gate, right? Okay, so then NOR gate, if I put a bubble at the output of an OR gate, then I will be having a NOR gate. So this is, you can see, whenever we have both zeros, we got 1, right? So you can see this is one sensitive. Whenever we have a 1, right, at any one of the input, we will get a low or 0 output, right? So this is the, say, NOT gate. If I compute this, this is the OR gate, right? And this is the AND gate, right? So this is, let me, A bar, B bar, right? So I will be having A bar plus B bar whole complement, right? So break the line, change the sign, A double bar, right, dot B double bar. So this is the functionality of an AND gate, right? Then we have another logic gate, that is XOR, right? So you can see that either A or B is high, we have a high output, right? So where we have a 0 whenever both the inputs are the same, right? So 0 0, 1 1, right? So either A should be high or B should be high, but not the both, because whenever we have both inputs high, we will get a 0, right? So this is another logic function, right? So you can see we represent this logic function with a plus sign with a circle, right? So this is plus sign with a circle, right? If I put a bubble here, I will have XNOR, right? This is the truth table, 0 0 1, right? 0 1 0 1 0 0. So whenever the two bits or two inputs are equal, right, so we will get a high. So this can be used as a comparator when we have to compare two bits, right? So here you can see we have a dot with a circle, right? Dot with a circle. So this is the representation of XOR gate, right? And then we talk about the simplification, right? Whenever we have to design a circuit, so we normally have to start from somewhere. We have a truth table that we have to implement, or we are given a Boolean function, Boolean expression that we have to implement. So, how we proceed when we talk about the simplification? So there are different methodologies, right? We can use Boolean axioms and laws in order to get the simplification, but the problem with Boolean axioms and laws is that there is no predefined number of steps or sequence, right? For example, if I have to pair two terms, right? So maybe I can group them at the end, or I can group them at the beginning of the simplification process, right? So there is no sequence, right? Or there are no predefined number of steps that I have to follow in order to achieve the simplification. But there is another methodology that is already predefined, and we have to follow predefined number of steps in order to attain the simplification. That is K-map, right? So here you can see that we have 2 and 3 variable K-map, right? So here we have 2 variable map, right? So here we have 3 variable map, and you can see that we have the min terms, right? So if we have a truth table having 2 variables x, y, and these are the min terms m0, m1, m2, m3, right? So if I place x in the vertical direction and y in the horizontal direction, so you can see 0, 1, y can always have 2 values, 0, 1. So this is 0, right? 0, 0, right? So this is x bar y, right? So x, y bar, x, y, right? If I talk about the 3 variable map, so you can see that we have I take y, z in the horizontal direction and x in the vertical direction. You can say x bar, y bar, z bar, right? So 0, 0, 0, 1, 1, 1, right? And 1, 0. So you can see that here we have a jump, right? Or you can say this is a sort of discontinuity. So in continuous way, we should move from 0, 1 to 1, 0 here, but we have a jump here. So similarly, you can see here m0, m1, jump, m2, m3, m4, m5, m6, m7, right? And then what we need to do after the mapping, right, from the truth table to the K-map, we will be looking for the groups, right? First, we will look for the maximum number of ones that can be grouped, right? So here we can have only a square, right? Then we will look for the pairs, right? So here you can see we are looking for the pairs, right? So these are the corners. So the corners can be replaced by this XOR functionality, right? So here we can see we have the K-map simplification, right? So then let's talk about the application of K-map. So we talk about a 1-bit adder, right? So in 1-bit adder, what we have normally, we have 2 bits, right? That has to be added, right? So here A, B, C in, S, C out. So this is the sum, right? And this is the C out, right? So you can look here. We have to add A, B, and C in, right? So sum 1, carry 0. If I look here, 1, 1, sum 0, carry 1. 1, 1, 1, right? Sum 0, right? And carry is sum 1, carry is also 1, right? So what I need to do, I need to design the circuitry for this. So I will be looking for the min terms, right? So I will be searching out the corresponding ones, right? And the min terms. So here we have a 1, so A bar, B bar, right? C in, A bar, B, C in bar, right? So this is the sum for C out. You can see we have 1 here. So A bar, B, C in bar, A bar, B, C in, right? And so forth, right? So here we are performing simplifications by using the Boolean laws, right? So you can see we have the K map, right? So we have a 1 here, 0, if let me write down the min terms, right? So this is M0, M1, M2, M3, M4, M5, M6 and M7, right? I will be writing the same here, M0, M1, right? M2, M3, M4, M5, M6 and M7, right? So we have a 1 here, right? That is M3, and then we have 1 here, M5, M6, M7, right? So we have mapped C out, right? So now we will be looking for the pairs. We have a pair here, right? And we can reuse the one which is already paired, so we can reuse that one. We have another pair, right, here, and finally we have this, right? So this is C out. So now we are looking, we are mapping the S, right? So 1, right, and then 2 here, right, and this is what, right, 4 and 5 is here, and then we have a 7 here, right? So here you can see that we don't have any pair, right? So for this one we have this, right? For this one we have this, because we don't have any pairing, right? And then we can have a K map for 4 input functions for 4 variables, right? So you can see that we have, if we have wx, y, z, so yz is taken along the horizontal direction, and or in the row, and in the column we have taken wx, right? So this is 0 0 0 1, so here again jump 1 0 1 1, right? So 0 0 0 1 jump, and 1 0 1 1, right? So you can see that we have the corresponding min terms over here, and here we have the numbering starting from 0 1 2 3 4 5 6 7. So from here we have to jump here, right? M8 M9 11 10 11, right? 12 13 14 15, right? So this is the K map for 4 variables, right? So here we can see these are the main terms, and in terms of 4 variable map, first we will be looking for a quad, right? So here we have a quad, then we will be searching for squares, and finally we will be looking for the pairs, right? So this is the pair, right? So we can also have the bending, right? So if I bend horizontally and then again I bend vertically, so I will be having this square, right? And then there are some conditions, right, where the digital system, right? So when we talk about a digital system, it often happens that the certain input conditions can never occur, right? For example, if we have a control switch, right, that has to control 2 interlocked switches, right, such that both these switches, they cannot be closed at the same time, right? So thus the only 3 possible states of the switches are both switches are open, right? This is the first one, and the second one is one switch is open and the other is closed, right? And the third one is the first switch is closed and the second switch is open, right? So namely, if you name them, so we can have 0 0 0 1 and 1 0, right? There is no 1 1, right? So we don't care, we can say that we don't care about 1 1 condition, right? So we can use the same don't care when we talk about the simplification using K-map, right? So here if we have a 4 variable K-map, so you can see we are looking different ones, and we are also having X that represent the don't cares, right? So we can place their zeros, right, or we can have their ones, right, whatever is convenient for us, right? So here we have a Boolean function, right, of 4 variables A, B, C, D, and these are the minterms and these are the don't care conditions, right? So you can see that we have the Boolean function, so we have the don't cares also, right? 6, 12, 13, right? So we have 1, right? So here you can see we have the simplification by using don't care. So here we have the X, right? So if I have not taken those don't care conditions into account, so I will be having a more complicated expression, right? So by virtue of those don't care conditions, I am able to have this quad, right? So I have taken those don't care conditions as ones, right? So I have the quad, and you know that by having a quad we have the maximum possible simplification, right? So we are only left with B as a result of this quad, right? And if I talk about this one, right, I can have a pair if I take this don't care as 1, right? So we have the scare by using this don't care, right, and I have taken this don't care as 1, right? So we have the, and then we have another covering, right? So we have this scare, this one, and this one, right? So I have not utilized as many don't care as here, right? So you can see that there is a difference. This expression has, right? So this is a 4 literal term, this is a 3 literal term, and this is a 2 literal term, 2 literal term, right? If I count the number of terms, right, 1, 2, 3, 4. Here we have 3, right? And if I talk about the number of literals, so we have more number of literals, right, here. Okay, then we have another example. I'm skipping this, right? So this is the same don't care conditions, right? So some don't care you use and some you don't, right? So here you can see that we are using this don't care, but we are not using this don't care, right? Because this is not favoring us regarding the simplification. So I will be having simplification when I use this don't care, right? I don't have any advantage whenever I talk about or I use this don't care condition. So sometimes you use and sometimes you don't use those don't care conditions, right? And then we can always have the NAND and NOR NOT network, right? Because the NAND and NOR, they are universal gates, right? You can have all the functionalities as we have seen by using those NAND and NOR gates, right? So here you can see we have the mapping. Here we have the AND and OR circuit, right? So and then here we have placed bubbles, right? So this is what? This is the NOR NAND, right? Then you can see that we have cancelled those bubbles, right? So what I did, I placed bubbles here, so those bubbles will be cancelled out, because this is what? This is the AND gate, right? And this is what? This is the OR gate. We have already proved that, right? But we can cancel those bubbles because double complement always cancel each other, right? So we are left with, this is NAND, this is NAND, so this is the all NAND implementation, right? Then sum of the products, so here you can see this is representing product, right, and they are being summed up, product of the sum, right? So these are the sums, they are being multiplied, so product of the sums, right? So we can have two-level logic using NAND gates, right? So here you can see we have two-level logic, right? First level is representing this parallel hierarchy, and this is the second level, right? So I have to go through quickly, right? So conversion between the forms, right? So here we can see that we have introduced bubbles, right? So this is the NAND, and this is what? This is because those bubbles, they are representing complements, they will cancel each other, right? And we have, this is what, this is the NAND gate, right? So let's talk about this, right? So we have bubbles, right? First we introduce bubbles, right? And then we balance them out, right? So here those bubbles, they will cancel each other, right? And here you can see we have to balance out, so we have introduced an inverter here, right? Another inverter here, and this is the bubble that is controlled externally, right? So now we have the all NAND representation. So these are the levels, first, second, third and fourth, right? First we will introduce the bubbles, right? So here two bubbles, two bubbles, two bubbles, right? And then we will be those, this is what? This is NAND, and this is also NAND. So now we have the all NAND representation, right? So I will skip this example, right? Right. So next analysis, right? So when we talk about the analysis, actually what we are doing, we are determining the behavior of a system given its description, right? So normally the circuit is described in the form of a circuit diagram, or you know the input and the output, right? And then we perform the analysis, right? So you can see that in the circuit analysis, right, what we need to find out the behavior of the circuit, right? So we normally apply all the possible inputs, right, and we note down the output, right? And sometimes we introduce the checkpoint if we have multiple levels, right? And we analyze the circuit, right? So here you can see that first we have to find out the input and the output, right? We must know the input and output of the circuitry, right? And then we can go either way. We can go for the truth table, or we can go for the Boolean expression, right? So we can also use certain tools in order to have the analysis. If you talk about the circuit design, right, so we need to go through certain number of steps, right? So these are the procedures, right? Design procedures, right? We need to determine the number of inputs and output, right? Then we can drive the truth table, or from that truth table we can obtain the Boolean function, and finally we have to draw the circuit diagram, right? So you can see, or you can think about that there is a very thin line between the circuit analysis and the circuit design, right? So this is the comparison, right? The design starts from the specification and ends up with the circuit diagram, right? On the other hand, analysis for a combination circuit is comprised of determining the function that the circuit implements, right? Or we can start from the truth table, right? Or we can start from the Boolean function, right? But there is one thing which we need to take care about, right? We have to make sure that the circuit which we are going to analyze is a combinational circuit, right? That there is no memory involved, right? Or there is no feedback. So let's talk about the adders, because when we talk about the computer system, there are certain operations that this computer system can perform, and addition is one of the operation, right? So we will start from the half adder, right? Whenever we have 2 bits, right, and we have to add them, so normally what we have 0 0, we have 0 sum carry, 0 1, 1 sum 0 carry, 1 0, 1 sum 0 carry, 1 1, 0 sum 1 carry, right? This is the decimal and this is the binary. So this here you can see we have sum 0 1 carry. If I have to draw the circuitry, because up till now we know the design and analysis, right? So here you can see we have to design this circuit by using this truth table, right? We have 2 inputs, 2 bits, right? This is the sum output, this is the carry output. So if I focus on S, right, so I have a 2 ones, right, 0 1 2, right? So let me write down the terms, right? So for this is M0, M1, M2 and M3, right? So I will be looking here, right, regarding the sum, right, here. So this is what? This is A0 bar B0, right, plus A0 B0 bar, right? And this is what? This is the Boolean expression of a XOR gate, right? So I must say A0 XORed with B0, right? So this is the sum. So here you can see we have a XOR gate, right? And for this carry we have 1 here, right? So A0 dot B0, right? So you can, so this is the half adder, but the problem here that it can add only 2 bits, right? So if I have to add more than 1 bit, right? So for example, if I have a binary number A and another binary number B, I have to add them. So on a piece of paper, what I will be doing, I will be writing down the numbers A like this, B, right, and then I will perform the addition, right? So 1 1 0 1 carry, 1 1 0 1 carry, 1 1 0 plus 1 1 1 carry, so 1 here. So you can see that carry is moving like this, right? So here we have a carry in, so this is the carry in, right, and then we have carry out, and this is the carry out, right? So Ci carry in, Ci plus 1 carry out, right? So these are the corresponding bits. So this is the bit by bit. So this is the full adder. You can we already know the idea how we design this full adder. So here if you look, we have cascaded 2 half adders, right? So this is 1 half adder, this is sum, this is carry, right? This is another half adder, sum and carry, and we have cascaded them, right? So this is the carry, right, and it is odd. So a full adder, here we have a full adder, 2 half adders are cascaded, right? Again, full block diagram of the full adder, 2 bits, right? And then we have C in, sum, this is carry out. And here we have a 4-bit adder, right? So we have cascaded full adders, right? So this is 0, you can see carry in, right? So sum, 2 bits, corresponding bits, right? So AB bits, numbers that has to be added, this is the sum and this is the carry, right? And then we can also represent negative numbers by taking 2's complement, right? So here is the circuitry, right? If for example I have to take add two numbers, right? For example, here I have to add a, that is a positive number, right? And I have to, that is a negative number, right? So what here, if I have e is equal to 1, so I will be taking the difference, right? Or taking the complement of that number b, right? And then I will be adding them up, right? So if e is equal to 0, then it will be performing the sum. So this is a 4-bit adder-subtractor circuit, right? So here you can see that we have adder-subtractor circuit, right? Okay, now we have to discuss the comparator, right? So if we have to compare two bits, right, a and b, right, and let us draw the truth table, right? So we have b in the row direction, right, and we have the a in the column, right? So here we have a is equal to b, both are equal, right? So here we have a 0, b 1, so b a is less than b, here a is greater than b, and a is equal to b, right? So this is the 1-bit comparator, but we are using these simple logic functions and or not, right? So we have the, if I talk about the min terms, right, so a is greater than b, we have only one, right, a b bar. A is equal to b, we have two possibilities, a is equal to b here, 0 0, a is equal to b 1 1, right? So a bar b bar plus a b, right? So here a less than b, a bar b, so this is a less than b, this is the only one. So this is the circuitry, and this is the 1-bit comparator. But we can also have a magnitude comparator, right? So there are three different possibilities when we talk about the magnitude comparator. Either a is greater than b, or a is equal to b, or a less than b, right? So if we have to work on this principle, right? So imagine that if we have a 4-bit number, right? So how many different possible combinations which we have to check, right? 4-bit a, 2 raised power 8, 256 different combinations which we have to verify if we talk about the comparison, right? So this is not a feasible one, right? So let's have the comparator. So here we have a 4-bit number, two 4-bit numbers. So you can see here, if a is equal to b, we will be having a 1 here. If a is not equal to b, we have a 0 here. How? For example, these two bits, they are not equal, right? So what will happen? Because normally when we talk about the XOR, so we have this Boolean function, right? So if a1 is equal to 1 and b1 is equal to 0, right? So here we have 0 and here we have 0. So as a result of this 0, we have a 0 here and we have a 0 here, right? But if we have all ones, right, all bits, they are equal, they are the same, we will be having 1 here, right? So but the problem is that how we can find a greater than b, right? So if we consider a this, b this, right? So here you can see that we start from the most significant bit, and we have seen that a and b are equal, a3 b3 are equal, then a2 and b2, they are also equal, but a1 is greater than b1, because here we have a 1, we have a 0, right? So we will be having c3 is equal to 1 and c2 is equal to, c3 is equal to 1, c2 is equal to 1, right? And here you see that a1 dot b1 complement, because here we have a 0, so we will have to take the complement in order to make them equal. So this is, then we will have a 1. So the next term will be c3, c2 dot A1 dot B1 bar in order to make all ones, right? So here we have a 1, right? So this will be 1 when we will take the complement, right? So this is the term, right? So if we generalize this rule, right? So you can see that we have A3 B3 bar, right? X3 A2 B2 bar, right? And so on and so forth. For this is for what? This is for A greater than B. And if I talk about A less than B, then we have A3 bar B3 plus X3. Now we are taking the complement of A's, right? So here we have B's complement, right? So here we have A's complement. So you can see that this is the algorithm which we can have whenever we talk about the comparison, right? Magnitude comparison, right? And then multiplexers, right? So we normally need to multiplex data from large number of lines onto a single line, right? So here you can see we have different inputs, right? And we have a single channel, and we have to transmit the data to a remote destination. So we have one link, right? So here these are the control switches. So whenever we have 0 0, this switch is connected here, so the data from here is launched here. When we have 0 1, see the switch or line is connected here, and the data from here is launched over this single channel. And then we have 1 0, then this line is connected and data from this line is launched onto this single channel. Finally on 1 1 we have connection here, and data from this line is multiplexed over here, right? So this is the functionality of a multiplexer. We want to route the data from large number of links onto a single link, right? So this is a 4-into-1 line multiplexer, right? You can see we need 2 switches in order to control the functionality. On 0 0, D0 will be selected. On 0 1, D1 will be selected. On 1 0, D2 will be selected, and so on and so forth. This is the quadruple 2-into-1 line multiplexer, right? So we have introduced more control by introducing enable. So right, whenever enable 0, irrespective of the S, right, select, or we will be having all zeros at the output, right? Whenever we have S0, right, so all A's will be selected. When we have S1, all B's will be selected, right? So the data from A portion will be at the output, right, when S0, and the data from B's will appear at the output when we have S1, right? Then we have the decoder, right? You can see we have n inputs, and we can have 2 raised to power n output, right? So this is the block diagram of our decoder, right? So this is 2-into-4 decoder, right? So you can see we have 2 inputs, 4 output, 0 0, F1 high, 0 1, F0 high, 0 1, F1 high, and so on and so forth. So this is the circuit diagram for this decoder, right? This is the block diagram, 2-into-4 decoder, right? Then we can have binary to octal decoder, right? So this is the binary, and this is the corresponding octal bit that is on, right? So 0 0 0, F1 is 1, right? So you can see we have all ones at this diagonal. So on 1 1 1, F7 is high, right? So this is 3-into-8 decoder. Then we have encoders. So if we talk about decoders, we have n inputs and 2 raised power n output, right? So this is the decoder. But if I go in the other direction, right? So 2 raised power n inputs and n output. On the basis of one of the inputs, right, only one of the output will be activated, right, in the decoder circuit. So this is 8 into 3 decoder, right? You can see we have 8 inputs, right, and 3 outputs, right? So here we have all zeros, right? So on the basis of this input, one output is activated at a time, right? Then we have D1, right? So this is 1, and here we have D5. So you can see we have 5, decimal 5 here, 4 plus 1, right? And this is 7, right? So D7 is high. So these are the equations. If we talk about the circuit design, so this is the truth table, and we can always find out the Boolean function from this truth table. If I talk about A0, so D1, right, D3, and then D5 and D7, right, A1, A2, right? Okay, so let's talk about the multiplexer. So this is the again opposite of a multiplexer, right? So here you can see the data from large number of different lines is being launched onto a single channel, right? And here this data is distributed, right, again here. So one thing we have to take care that the time slot has to be synchronized, right? The time for which this switch is connected here should be the same, right, whenever we distribute the data from single channel to those different lines, right? So here we have a 1 2 multiplexer, so we need a 1 switch, S is equal to 0, D0 will be selected, right? So when S1, D1 will be selected, right? So here we have 4 into 1 to 4 DeMultiplexer, right? So you can see that we need 2 control switches, S0, S1, 0, 0, D0 will be selected, right? Data will be distributed to the D0 line, and whenever we have 0, 1, D1 will be selected, 1, 0, D2 will be selected, and so on and so forth, right? So that's all for today's lecture, right? So we have a recap, right? So next time we will be starting the sequential logic, right? So that's it. अपना ख्याल रखिएगा. अल्लाह हाफ़िज़.